Selection 9, corresponding to Lab 9, is LDA. Well, we'll first start talking about LDA in this lab. We'll finish up talking about it a bit in next lab. But today we just want to do a real quick recap of LDA in kind of a one-dimensional case where we have 1x. So this is Lab 9 on LDA, and we'll grab some packages we'll need for plotting a little bit later. What we're going to do in this lab is I'm just going to generate some artificial data. And what I'm going to do is we're going to generate a data frame with 3 groups, group 1, group 2, and group 3. And we're going to sample from 3 normal distributions with means all have variances of 1, but the group 1 has mean 1, group 2 is mean 5, and group 3 has mean 20. And we're going to get 100 points from each of these. And so all we do is we generate these 3 sets and we bind them together. And we're going to make our grouping variable a factor. So notice that LDA is this generative model, and the way we generate our data is from the class conditional distributions, right? I'm saying this is the class 1 distribution, is normal with mean 1. So given I'm in class 1, I'm assuming my x's come from normal with mean 1. Given I'm class 2, they come from normal with mean 5. And given I'm in class 3, they come from normal with a mean 20. So if you go back to how LDA is written, these are basically the class, and this is the distributions of x given y. Given y is 1, 2, or 3. So this is my data. We can just take a peek at what this looks like. So it's just a data frame. Actually, let's sample. How do I want to do this? Can I just do that? Nope. Let's just randomly sample some rows from this, just to get a sense. So they have a grouping variable, 1, 2, or 3, and then they have some values. And we can plot what this looks like. Let's only look at the first couple of those, right? We can actually plot what this data looks like. So here I'm just going to plot a density plot, and I'm going to plot on the x-axis x, and I'm going to group them by grouping variable. And I'm going to add in some points, and let's just look at what this plot looks like. So here's my plot. So it's a density plot. So here on the x-axis, so this is one-dimensional, right? If we go back to our data, we just have a 1x, right? P is 1. And so I get my points here on the x-axis correspond to my training points. Some of them are over here. My group 1, which is the red, has a mean of 1, so my points tend to cluster over here. My group 2 with a mean of 5 tend to cluster around 5. My group 3 with a mean 20 tend to cluster around 20 here. And we have density plots. If the y-axis is the density, we have the density of the 3 groups. Just some estimate of the density. And you can see they kind of separate. 1 and 2 are close together, but 3 is a little farther away. So we can write our own LDA function. All right, so LDA, the way you write it is you can define the discriminant function for each of the classes, delta C for class 1, 2, and 3. And then you apply that to a point you want to predict, and you figure out which one of those things has the largest value. So here is our example. Maybe my point I want to predict at, let's call it x0 is 1. So it's somewhere around here. Presumably it's most likely going to be from class 1. That's what we expect. And so if I were to fix my class variable 1, I could calculate my delta C of 1. So how would I do that? So let's just let's comment these out for now. First thing I have to do is I'm just going to grab the data from group 1. So I'm just going to grab all the group 1 data. If you remember the formula, what the parameters I need is I need the means for the groups, I need the overall variance, and I need the prior probabilities, the pi's for the groups. So my mu hat for group 1 would be just the mean of these things, right? and it's about 1. So this is of my training data. We're not, in this lab, we're not going to get into training testing. We're just going to do everything in the training data, right? So this would be my mu1. I need a sigma hat. I'm not going to go quite into the code here. This is actually going to be sigma, not sigma squared, right? So I need my sigma hat. All I'm doing here is this is just some pooled variance estimate. So the reason why it's not simpler, or in this case, pooled standard deviation estimate. So a pooled estimate, right? How do if I assume that these 3 classes all share the same variance, what I don't want to do is just throw them all in the same pot and calculate the variance, because that variance will capture not only the within class variance, right? My sigma squared is really just within group 1 what's the variance, within group 2 what's the variance, within group 3 what's the variance. It's not the fact that there's a mean difference among them. So what I first have to kind of do is I mean center each of the 3 groups, or I calculate the variance of each of the 3 groups separately, and then I just take the weighted average of them. So that's probably the best way. It's just, a pooled estimate is basically, what I'm going to do is I'm going to calculate, this first thing says calculate the variance of the 3 groups separately. I'm going to take the mean of those 3 estimates. In this case, I can just take a mean because I know that I have the same number of points in each of the classes. If you had a different number of points, you would have to take a weighted mean. And then I want my standard deviation, so I'm gonna call it, I'm just gonna take the square root. Okay, so that would be sig hat, which should be about 1, right? And indeed, it's also about 1, because we know when we generate their data, the variance of these was 1, so the standard deviation should be about 1. And then I need my pi hat. My pi hat is just, if in this case, we're looking just at class 1, I need this to be just the number in my training data points in the class. In this case, class 1. The easiest way to do that is just say mean of group is equal to class, right? So this is going to, if I just look at, let me just back up here. If I look at D sub group equals what my class is, it's going to give me a bunch of trues and falses. And if I take the mean of that, it's going to give me the percentage of them that are true and false. In this case, we knew that a third of them came from class 1 in this case, because we generated it that way. But this would be my pi hat. And once I have those estimates, my LDA, my delta function, my discriminant function, was of course just this Bayes probability, right? It was a certain probability. And I can calculate with that with D norm. So that gives me the density of a normal distribution at the point I want to predict, with a mean of my mu hat and a standard deviation of my sigma hat. And then if you remember, I multiply, if you go back to the formula, multiply by pi c. So in this case, this is pi 1, sigma hat, and mu 1. So this is one way we can definitely define our, this would be delta c at 1, delta 1. So normally it's delta 1 of x, and this is delta 1 of x naught, which is 1 in this case. And that would be the value for class 1. You can change it to class 2. It would give me a different value in class 3. It would give me a different value. You notice the values for class 2 and class 3 are small, and class 1 is high. So our predicted value would be, a predicted class at 1 would be 1, which makes sense, because if we look at our data, if we're predicting what class we expect to be at, say, wherever 1 is over here, well, that's that according to our distribution, that's much more likely to come from group 1 than it is 2 or 3. So you can actually just throw this to a function called delta LDA. You give it my x I want to predict at, you give it the class, so this would be 1, 2, or 3, and it will give you the value. So if I want, and what you do, if I want to predict at 1, or maybe I want to predict, let's say, at 5, you know that, so 5 is basically right in the heart of these greens, should be that the discriminant function for the second discriminant function for class 2 should be the highest. We calculate all of those, and indeed the discriminant function for the second class is the highest one, and that's the one we should choose, right? Oops, I want to change that. You could change it to another 0.7. You could recalculate them all. It's still going to be highest for class 2, because 7 is pretty close to these. Is according to the model, 7 is much more likely to come from class 2 than 1 or 3. So that's one way of defining so this is literally my discriminant function. We just written it by hand, and what you do is you would say which.max of these three things, and that would be my y hat, right? Of course, that's not how which.max works. Let's try it like that, and there you go, class 2. That's my estimate. So that's the entire LDA procedure. Super, super, super simple. Of course, we did a second derivation where we showed there's a second way of writing the discriminant function, and that was like mu hat times x naught over sigma hat squared, right? This is this other thing, right? So you could also define it this way, but we claimed that these were, one-to-one functions of each other, and so I could instead use my second version. Right, we had taken a log, we had thrown out terms that weren't useful. This is kind of the final form we had derived for a one-dimensional case. And again, we'll get the same y hat. Okay, so of course, so I could predict on my training data by basically applying my 1, 2, and my LD, my delta function, my discriminant function to data for class 1, 2, and 3, and then looking at predicted values. Let me just say sample 5 of these, right? So this is just how you apply it to all the training data. Of course, in reality, we don't have to write the LDA function itself. There is an LDA already written for us in R under the mass package. So if I load up mass, I could query LDA, linear discriminant analysis, and the function is LDA, and it operates much like regression, where, so here's how you call it. I say my model is LDA. I'm going to have my group, which I'm trying to predict, is going to be predicted from my x, and I give it my data. And you could predict, let's just get rid of this line for a second. In fact, there might be a summary version, so I can get the summary. Nope. There's no summary version for this, but there we go. That would be my model, and so the prior probabilities, it gives me my group means, which I had calculated by hand, so you can check that these are the same. It should give you the pooled standard deviation estimate somewhere, and you can predict it. Let's just move this down here. You could predict it with predict function. So I call predict on my model, pass it the data, and I want the class, so I'll tell it to grab off the class. Those would be my model predictions. Right? Is that going to work? Mod pred. Okay. So those are my predictions, and you can actually test that this gives us the exact same thing as our homegrown one, as our home brewed one. So same answer as our own version, right? And one way I can check that is, let's make it a little smaller. One way you can check that is you can just convert the predictions from the LDA function are factors, hence you see this little levels thing here. You can convert them into integers, and you could sum up, you would ask, what's the percentage of them that don't match? And of course, it's 0%. They all match perfectly. So in the last minute or two here, I'm not going to go through this code in detail, certainly not today, but I wanted to just show some plots. So here again is our data, and I've written some visualization code to visualize what LDA is doing. So here is our first LDA 1. So maybe let me write this here. LDA discriminant functions. All right. So here are my discriminant functions. There are multiple versions, but here are some of my discriminant functions. This is basically what it's fitting. LDA is basically fitting 3 normal distributions with the same variance to each of my groups. And then it's just going to look at, well, it's going to predict red over here. So that's why I've red my x-axis, because the model, the normal I fitted the data over here has a higher density, high probability, until I get to this point where I cross over, I start predicting green here. So I have green on my x-axis because the model fitted to the class 2 points. This normal model here has a larger probability or a larger density. And that's true up until I get to this point, and then we start predicting blue because the normal model I fit to my third class is larger. But these are, you could either think of them, as my probabilities, my Bayes classifier, or they're the discriminant functions. And I pick if I'm predicting over here, I pick the class with the highest discriminant function. Well, the discriminant function of red is clearly higher than green or blue. It's higher for green over here, etc. Of course, we did a transformation, we could look at discriminant functions for our second version, right? So what we had done is, our second version was to go back up, which is actually what R is using at the end of the day. R is not actually calculating normal probabilities. Way back up here, right? So we had two versions. The first one used this normal, actually calculated the normal density. And the second one, we did this transformation, this derivation in class, and showed that it's actually linear, right? There's a slope, which is like mu hat over sigma hat squared, and then this is our intercept term, right? And so we claim that this thing is linear. And so when you look at these discriminant functions, you say, well, the discriminant functions aren't linear, but we claim there's a transformation that makes them linear. And so you could actually plot that second version, which gives you the exact same classifier, just discriminant functions look different. If you compare these two figures, the places where we predict the three classes that it's going to indicate in my x-axis is exactly the same, but we can see in the second version, which is just a transformed, a monotonically transformed version of our other discriminant functions, these are all linear functions, right? They're just linear in x, and they have different slopes, and so over here the red is the largest, and here the green is the largest, so we predict green, and here over here the blue is the largest, we predict blue, right? And they change where green and red predict, that's where our change point is, that's our decision boundary. Where blue and green intersect, that's where we get the decision boundary here. So it's a nice little visualization of what LDA is doing. Okay, so let's call it there.